Well, welcome to the Fundamentals of Particle Technology, Chapter 8, Question 2, which is about continuous tube-type centrifuge. And this probably actually follows on better if you were to have just done the problem on in Chapter 5 on the Camp Hazen settling basin, because in the Camp Hazen settling basin, which was question 2, I think, from Chapter 5, the plan area of the settling basin was calculated, and the sort of logical follow-on question is supposing you actually don't have sufficient plan area available in order to construct a settling basin to remove the particles that you wish to remove. What can you do? What's the next step up, in other words, in terms of process intensity above a settling basin? A settling basin uses a field force which is free, that's gravity and weight of the particles. Clearly we need to use an enhanced field force to speed the process up, and that is exactly what a tube-type centrifuge would be doing. It's enhancing the field force and making the device much, much smaller for the same throughput. Okay, so looking at the continuous tube-type centrifuge as an alternative to the settling basin, the similarities become even greater. But let's start with part 1. Part 1 is fairly straightforward, because part 1 just really asks us to convert 5.4 meters cubed per minute into meters cubed per second. The SI unit's meters cubed per second. So back to the trusty calculator. That's not too difficult. We need 5.4 divided by 60. So that is 0.09 meters cubed per second. So the volume flow rate is 0.09 meters cubed per second. I mean, the question 2 is really asking is calculate the sigma value, and I'll explain that in a little bit in a moment. For this particular centrifuge, calculate the sigma process. Part of the calculation is, well, in fact, actually, it's probably a good idea to put down, let's see, we've got a bit of space down here. Let's put down here what sigma process is. I mean, big capital sigma process, I'll just call that sigma p, is equal to the volume throughput that we've just calculated divided by the terminal settling velocity. Okay, and that is equal to the plan area of a settling basin. If you have a look at that question at the end of Chapter 5 that I was just talking about, the plan area of a settling basin is Q over UT. So the sigma process, exactly the same. Volume throughput doesn't assume a centrifuge necessarily. UT certainly doesn't assume a centrifuge necessarily. Then Q over UT is the plan area of a settling basin, or the equivalent plan area of a centrifuge. So we're using sigma value as the equivalent meter squared area as a settling basin. So we do need to calculate UT for sigma process. So if we come over here, and UT is going to be equal to, yeah, that just about fits in below my happy smiling face, x squared density difference times by g, all divided by 18 mu, which in our case here, because we're dealing with 10 micron particles, so that's 100, but times 10 to the minus 12, so that becomes 10 to the minus 10, 10 to the minus 10 in meters, because we've got a 10 micron particle which squares to 100, but that's 100 times 10 to the minus 12, or 10 to the 10. The specific gravity is 2.8 and the liquid is 1.0. Specific gravity, remember, is relative density, so that's 2,800 kilograms per meter cubed equivalent density, and that is the density of water, 1,000 kilograms per meter cubed. So down here we know we've got 1,800, which is the difference between the two, and of course we've got 9.81 for G, 9.81 for G, and that is all divided by, interestingly enough, 18, so there's something that's going to be cancelling there, times 10 to the minus 3 for the viscosity of water. Quick check, yeah, there it is, 10 to the minus 3 viscosity of water. So clearly we can cancel that with that. That brings that down to 10 to the minus 8. We've got another 3 there, so that's 10 to the minus 5. 9.81 times 10 to the minus 5. I can put my calculator away for that. 9.8 times 10 to the minus 5 is answer D, is there. Well, we're using Stokes's law, so we better just check that Stokes's law is valid. For that we need the particle Reynolds number, which I'll clear a bit of space because I'm going to stay here rather than scroll around. For particle Reynolds number we need the du over mu, the usual form for a Reynolds number. Particle Reynolds number, that linear dimension d, is the actual size of the particle, the diameter of the particle. So particle Reynolds number is equal to the diameter of the particle, the terminal settling velocity we just calculated, and if I keep these two together, because they will equal 10 to the power 6, then that means I'll come over here for the equals. We have 10 to the power minus 5 meters. We have a velocity of 9.8 times 10 to the minus 5, and with a density of 1,000 and a viscosity of 10 to the minus 3, that is all multiplied by 10 to the 6. So that quite nicely cancels out some of those minuses. So we have 9.81 times 10 to the minus 4 as the answer for the particle Reynolds number, which is answer D again, actually, 9.8 times 10 to the minus 4. Okay, so that's massively less than the requirement of Reynolds number, particle Reynolds number, being less than 0.2. So we're easily in the laminar or streamline flow around the particle region, because there's very little turbulence in this system, because the particle Reynolds number is so low, well below that threshold of 0.2 for the validity of Stokes's law. Okay, so we know what the volume flow rate is. Meters cubed is 0.09 meters cubed per second. We know what the terminal settling velocity is. So let's just put that into our calculator. So we're talking 0.09 divided by the velocity, which is 0.123495. Sorry, 98, which is 918, which I guess is pretty close to 920 meters squared. So the sigma process for this device is 920 meters squared. In other words, this centrifuge is equivalent, does the same job as a settling basin that is 920 meters squared. So put that into context, well, if you had a 10 metre, this is plan area, if you had a 10 metre wide settling basin, it would have to be something in the order of 92 metres long. So that, as a gravity settling basin, would do the same duty as this centrifuge in terms of removing all the particles that are 10 microns in size and above. The centrifuge dimensions are actually given in the next question, so you can see, or you will be seeing, how much smaller footprint the centrifuge is compared to this gravity settling basin that we're replacing courtesy of this particular centrifuge. Okay, thank you.